Hi, this is Nathan, and I was asked to do a couple of videos explaining multivariate central limit theorem and multivariate delta method, so that's what I'm going to try to do in the next couple of videos. First off, I want to do a video on the multivariate CLT. And talk a bit about where that comes from, and I feel like sometimes the notation gets very heavy, so hopefully clear up some confusion on that. So we have the CLT, so univariate case, which states that if we have x1 to xn iid, note that each xi, each one of these guys, is a random variable, iid meaning they're independent and identically distributed, right? And they have a mean mu, which is finite, and variance sigma squared, which is also finite, right? Then the CLT states that the sample average of these n samples, or IID samples, minus the mean over sigma, so the standard deviation divided by n, converges in distribution to z, where z is the normal distribution with mean 0 and variance 1. Now, a couple of equivalent forms on this that you can get through some easy algebra. You have square root of n of x bar minus mu over sigma converges in distribution to z, or the one that we will be replicating with the multivariate CLT is square root of n x bar minus mu converges in distribution to normal distribution, the mean 0, variance sigma squared. We just multiplied the sigma over and you have to square it. Okay, so let's talk about the multivariate CLT. Now we have x1, x2 to xn, right? Except each xi is, instead of a random variable, it is a random vector. What do I mean by that? So each xi is going to be a vector, so a collection of random variables. We'll call it, so let's call, for xi, we will call it y1i, y2i to ymi, right? Didn't make these brackets quite big enough. So each yi inside each xi is a random variable. So each xi is a collection of random variables, right? So now we have that x1, x2, and x up to xn, all of these random vectors are IID, meaning that each x1, x2, each one of these vectors is independent of one another. That does not mean that inside one of these vectors, each yi is independent of one another. For example, y1i and y2i are not necessarily independent. They could be, but they don't have to be for this to work. But each vector xi is going to be independent from each other vector xi. So the random variables inside x1 will be independent of random variables inside of x2, and so on. And for the MV-CLT, we have, for the univariate CLT, it has mean mu. We will have the mean vector mu, which is going to be mu1, mu2 to mu m, because we have m random variables. So each one of these random variables mean is expressed here. And the covariance vector is going to be expressed as sigma. Now, I got a question, what is the covariance vector? Just someone wanted clarification on that. So, going to try to express that here. What the covariance vector is, so this is we have covariance of y1, y1 here. We have covariance of y1, y2 here. Work your way down. So covariance of y1, ym here. I really did not give myself enough space. But then this next entry would be covariance of y2, y1, covariance of y2, y2, to covariance of y2, ym. And two properties of covariance that are useful or make this covariance matrix more useful, I guess, are one, covariance of y1, y2 is equal to covariance of y2, y1. So this matrix is going to be symmetric about the diagonal, right? And two, the covariance of y1 and y1. So the covariance of something with itself is equal to the variance of y1 in this case, or the variance of the thing. So that means in our case that on the diagonal, which I really, again, did not draw very well here, but on the diagonal we will have all of the variances, and then next to the diagonals we'll have all of the covariances of the different terms. Okay, so for the MV-CLE, we have these components, right? Now, last thing we need to talk about before I can give you what the MV-CLT is we're going to have a vector x bar, right? And this random vector is going to be the sample mean of all of the y1s and the sample mean of all the y2s up to the sample mean of all the ym's. Because in the first place we have the y1s and the y2s up to the ym's. Right, so this is like all of the sample means expressed into one vector. Then we have, and this is the multivariate CLT, finally, we have square root of n times x bar, this matrix here, minus mu, the mean matrix, converges in distribution to a multivariate normal distribution with mean vector 0 and variance sigma. Notice that this sigma is the original covariance matrix that we had from the beginning, right? Which is very similar to what we have in the CLT, because we had that just underlining it, that this left-hand side converges in distribution to a normal distribution with mean 0 and the original variance. Just like that, we have that this left-hand side converges in distribution to a multivariate normal. It's multivariate because it's a multivariable. We're using vectors instead of random variables, right? With mean vector 0, which, by the way, it's going to look like this, It's going to be all zeros. And the covariance matrix is going to be a sigma, the original covariance matrix.